Hi, this is David Bonacciaro. Welcome to the third video in the market risk measurement and management topic. This video is 5C. It published on March 10 and can be downloaded at any time. So we continue in sequence with the study guide. That means we have two chapters that reappear from Jorion's textbook. So again, not the handbook. The handbook formally does not appear on the Ames. So this is the third edition of the Value at Risk, and two chapters that reappear on Value at Risk, backtesting and VAR mapping. Not long chapters, although we know from experience that these are dense chapters that do give some difficulty and challenge to new learners, new exposure to VAR. And unfortunately, I can't really speak to the testability because while they've been assigned, and historically they've been assigned, frankly, their manifestation on the exam has been pretty low, especially with the VAR mapping, because another one of those topics is difficult to fit into a 3-minute quiz. And so, of course, we need to be familiar with them, although I wouldn't recommend spending an over amount of your time on these topics, especially the VAR mapping, unless you have another agenda. But if your agenda is the exam, I would frankly give the VAR mapping the superficial treatment that it deserves. And so, as usual, learning spreadsheets associated with this, 5C1 and 5C2, VAR backtest and VAR mapping, and they are really where I've replicated examples in Jorion's chapters. So we start with Chapter 6, define backtesting and the exceptions and explain the importance of backtesting VAR models. So model validation is the process of checking whether a model is adequate. And then in terms of just the definition of validation, Jorion has as types of that, of model validation, backtesting, stress testing, and independent review and oversight. And so in this chapter, we're most concerned with backtesting. Stress testing he devotes to another chapter. And so backtesting is specifically when we compare actual historical losses to projected losses. So a backtest really implies that we have some historical performance, a historical database in order with which to evaluate. So a key term here is exceptions, or depending, synonymously, exceedances. So exceptions are the number of loss observations that exceed the VAR. And hopefully this is familiar because when we defined VAR, right, we said that, for example, a 95% VAR means 5% of the time we expect the loss to exceed the VAR. So exceptions, the existence of exceptions is not a problem itself. We expect exceptions. The issue is how many. Do we have more than we would expect from an accurate model? So for example, if our VAR model is perfectly calibrated, then a 95% daily VAR, and notice I color code that because notice how succinct that is, the specification of a value at risk. Remember, we've always said there's two design decisions, a confidence, which could just as easily express that as a 5% significance because we know it's one-tailed. So we've got the confidence and we've also got the horizon. When we say VAR, it really helps to have a complete and precise specification. We want the confidence and the horizon, and we've got that there. So a 95% daily VAR should be exceeded about 13 days per year. How do we get that? Well, we assume 250 true trading days per year, and we decided to set our VAR, or we produced our VAR based on this calibration. So we expect 5% of the time losses to exceed the VAR. We expect 5% exceptions, or 5% of the 252, or 12 or 13 would be about the mean expectation for the number of exceedances. So you can see that's still quite a few. A 95% daily VAR expects quite a few exceptions or exceedances during the year. Now, if we want more confidence, then that daily VAR number is going to be, that loss number is going to be higher, and we're going to expect that to only be exceeded about 8 days or 3 times. Or I'm sorry, I changed my 95% daily VAR should be exceeded about 8 days in a 3-year period. 3 years times 252 trading days times the 1% significance equals about 8 exceptions. So the two backtesting difficulties are we have the historical database, but if we think about our econometrics, a historical data set is just a sample. It's just a sample we happen to experience. So this backtesting remains an uncertain statistical decision. Do we accept, do we reject the model? And with the possibility that we can create two kinds of errors. If we accept or reject, we always have the possibility of either a type 1 or type 2 error. Second, the actual portfolio is contaminated by dynamic changes in the portfolio composition. But VAR, this basic variation of VAR, assumes a static portfolio. So in Jorion, we verify the model by recording the failure rate. And our null hypothesis is that the model, the VAR model, is correctly calibrated, where the number of exceptions should follow with a binomial probability distribution. That's sort of the elegant feature of our use case here. If we think about it, we either have an exception or not, meaning a loss that exceeds the VAR threshold, or it does not. That's two outcomes. That's a Bernoulli. And if we have several days of these Bernoullis, we have a series of Bernoullis. We can characterize this with a binomial probability distribution. And so, for example, if we employ a 99% VAR model, that means we expect daily losses to exceed the VAR on 1% of the days. So a statistical question, for example, would be, now this is the example of starting the back test. Let's say over the last year, the 252 trading days, we observed 4 exceptions. 4 into 250 should be about 1.6. So I take 4 divided by 250. I get 1.6%. And so notice our VAR significance was 1%, yet we observed exceptions on 1.6%. We were sort of expecting 1%. And so this is really a classic statistics issue, right? Because we've observed a sample. It's possible that our VAR model is accurate, and it does, and that it has that the true population value here is 1%. And just because of the sample that we happen to observe, due to the random sampling variation, we got a higher number. So the issue is that additional plus 6 merely due to random sampling variation, or does it implicate an inaccurate VAR model? Can we know the answer? Can we know the answer to that? Can we know the answer to that? Well, we can't know with any certainty. We can either decide where we want the error bias to be. We can be conservative and reject this model, or reject the null that the VAR is correct. And notice when we make that decision to reject the null, we do run the risk of a type 1 error, which is to reject a VAR model that is actually correct. Or we can be aggressive and decide to accept the model, but here also we run the risk of the other kind of type 2 error. We run the risk of accepting the null when the null was false. So proceeding to the actual Jorion example, and illustrated also in the Learning Spreadsheet 5C1, he shows 2 possible truths. So this is really, in the left and right panel, the truth of the underlying model. Here under P, probability of 0.01 on the left-hand side, where the null hypothesis is true, or to put another way, when the VAR model is accurate. So if the 99% VAR model is accurate, then the distribution of our exceedances when T equals 250 trading days, and notice I've switched from 252 to 250 here. I don't think that makes a big difference. Then we've got a binomial distribution here that characterizes the number of exceedances we would expect for a 99% VAR model that's accurate. And so this here on the left panel really illustrates the random sampling variation. The fact that this accurate 99% VAR model could exhibit 0 exceedances fully 8% of the time. After all, if the mean is 2.5 it's possible that we just get lucky over the whole year and there are 0 exceedances. On the other hand, even this accurate model for this sample size of 250 can exhibit 5 exceedances, again, losses in excess of the VAR, fully 6.7% of the time. So this goes to the fact that we're looking at a sample. Even if the model is accurate, we're going to get some distribution here. And then Jorion's other case is a VAR model that's not accurate, and it's harder to model this because the not accurate model, we don't know, it could have any number of imprecisions, right? We're assuming, or we've calibrated a 99% VAR, so we know what an accurate model would look like in terms of the p-value here, the significance or probability. But the inaccurate model, in Jorion's example, has a 3% significance, but notice that it could be a 4%, 5%, 6%. A really awful model would be 10%. So we actually have an almost infinite number of incorrect models to use as a basis here. But notice the red zone, even this inaccurate model, and again, what we mean by an inaccurate model here on the right panel is that we calibrated a 99% VAR, but we're really using a 97% VAR. So that model, although inaccurate, also has a binomial distribution, and then notice, although its mean is going to be higher, it also, due to random sampling variation, could produce a low number of exceedances, even 1 or 2 or 3 exceedances with only 3.8%, with fully 3.8% probability. So you'll notice here, this speaks to the uncertainty. When we take a sample, just as the accurate model can produce a lot of exceedances, so can the inaccurate model get really lucky and produce a few exceedances. So if we observe 3, it's possible, it's more likely that we're dealing with our accurate model, but it's certainly possible that we have an inaccurate model. In another visual look at the same kind of trade-off decision that we're making, here the correct model and the binomial distribution associated with a correct model that has with 99% confidence, such that we can decide if we observe 5 or 6 or 7 or 8, let's say we observe 7 exceedances, we're going to decide to reject that model. But we do run the risk here of a type 1 error, to reject this model when in fact it is correct. And conversely, if we have an incorrect model with a true VAR of 97%, and we only observe it gets lucky and only produces 3 exceedances, we might rightly decide to accept that model, but we've committed a type 2 error. So here's just a focus in on Jorion's box 6.1, where we use that binomial distribution and then approximate it with a z value, so that binomial starts to approach a z. And you'll notice this is fairly resembles our the way that we compute a standard normal variable. We've got the observation x minus the mean value, so that distance between our observation and the mean, divided by here the standard deviation of the binomial of the binomial variable, p times 1 minus p times t. What's in that parens is the variance of the binomial with t trials. We take a square root of that to get the standard deviation. So you notice how we've really, this is the formula for computing the z variable based on a standard normal distribution. So that's the meaning of this notation here. It approximates the standard normal with mean of 0 and variance or standard deviation of 1. So this allows us, with some confidence level, to decide what the cutoff is. In this case, the cutoff in terms of the number of exceptions. And so we've seen that we can commit 2 types of errors. The probability of a type 1 error is, we can call that alpha, the level of our significance. So that's what we specify with the 1 or 5%. And then there is a probability type 2 error beta that's much more difficult to calculate. Why is it necessary to consider conditional coverage in the backtesting framework? Unconditional coverage ignores time variation, but our actual exceptions could tend to cluster. Sort of reminds me of unconditional volatility and then the Garch model treating volatility as conditional because time varies. So in the Basel rules for backtesting, a number of exceptions are observed for, in this case, a sample of 250 observations. And then that green, yellow, red zone in Basel, also called a stoplight or traffic light, I think, is really just an acknowledgement of that same uncertainty in the trade-off. So there's a green zone where a low number of exceptions is enough safety such that we decide to accept the VAR model as accurate. With a large number of exceptions, there are too many, and so we decide to reject the VAR model. But in the yellow zone, we have that trade-off between the type 1 and type 2 errors where there's really material probability of committing either of the errors. So Basel carves that out, the committee carved that out and allowed as a way to help mitigate this statistical problem, allows for some discretion there. And the supervisors asked to look at the causes and then make a decision. So if we look at Chapter 11, VAR mapping, mapping replaces a current portfolio of position values with exposures to risk factors. Why do we need to map? Large-scale aggregation is too complex and time-consuming to model all the positions individually as risk factors. So mapping principles include many positions can be simplified to a smaller number of positions on a set of primitive or elementary risk factors. And this is the only solution when instrument characteristics change over time. For example, when the risk profile of bonds change as they age, we cannot directly use the history of bond prices. Instead, we want to map to yields that best represent the current profile. So the basic generic steps are 1, mark all positions to market value, and 2, the market value for each instrument is allocated to the risk factors. So according to Jorion, there are two types of mapping: exact allocation of exposures on risk factors, or, if not exact, estimated. So visually, if we have a portfolio with several instruments or positions, the idea is that instead of dealing with all of the complexity of all of the different positions, we're taking each of them and mapping them to a limited number of risk factors, and we can manage and model the risk factors more easily. And so stylistically, if we have several instruments in our portfolio, if each instrument has a market value, and then we identify that as a superset there's exposure on 3 risk factors, we take each of these instruments and map its market value to its exposure on the different risk factor. So this instrument 1 gets mapped to exposure to primitive 1, excuse me, then primitive 2, then primitive 3, same as instruments 2. Then we come back and notice vertically we can say the first primitive risk factor is exposed by has exposure from each of these different instruments vertically. Then the total portfolio here, as the sum of these, the total portfolio has exposure on this one risk factor. So in a way, we've taken several instruments here, 6, remapped the portfolio total market value to say that the total portfolio and market value maps to the 3 risk factors. Specific risk is the risk that's inherent to the company or security. Elsewhere, we've called this idiosyncratic risk. So it is issuer specific as opposed to market related. One of the points here is that a greater number of general risk factors should create less residual risk. So we think about that market model or the capital asset pricing model, and if we want to take a simple perspective and say that the risk of the security of the portfolio is a function of a beta or sensitivity to a common market factor plus something idiosyncratic, then the idea is then if we only have the one factor, a lot of this variability may show up as idiosyncratic risk. Sort of like a single variate regression or multivariate regression where there's omitted variable bias. Maybe there's another factor that's really hidden in this idiosyncratic risk factor. So we figure out what the other factor is and we add it as a common factor. Now it looks more like multi-factor CAPM or APT. And then we've got exposure to an additional factor. And as we increase the accuracy, as we do that, increase the characterizing the risk as exposure to systematic factors or common risk factors, then we should reduce the amount that can be attributed to the specific or idiosyncratic factor. So Jorion's three methods for mapping portfolio of fixed income securities includes principal mapping, duration mapping, and cash flow mapping. Principal mapping and duration mapping are both single factors. So keep in mind, we're talking about a portfolio of fixed income securities or bonds. In principal mapping, where the one risk factor is the principal, and we're looking at the average maturity of the portfolio. In duration mapping, the one risk factor is portfolio duration. Recall that portfolio duration is the weighted average of the component durations. So it's really, if we have each of the individual durations, portfolio duration is just as easy to compute as weighted average maturity. And so here, the single risk is a zero coupon bond with maturity equal to the bond duration. So those are the two simple cases. Principal is really simple and maybe unnecessarily naive since we can avail ourselves of duration mapping. And then cash flow mapping goes beyond the single risk factor into several risk factors where we decompose the bond into each of the cash flows. So with respect to mapping the fixed income portfolio, there is a previous exhibit in Jorion 8.4 that I thought important to include because it sets up the fixed income portfolio mapping. And then again, as a caveat, I can't speak to the testability of this. The level of detail outpaces the ability on the exam of GARP to fit into a 3-minute question, and generally seems to be the case historically so far. So just really unclear about the strategy for testing this chapter, unfortunately, even after it's been assigned for so many years. But in spreadsheet 5C2, I have these calculations replicated from Jorion, and 8.4 sets up the risk of the bonds, right, based on our linear approximation that a returns-based VAR is going to be equal to a yield VAR times the modified duration, right? So that's the variability in our price is going to be a function of yield times modified duration. That means yield VAR should be about equal to returns VAR divided by modified duration. And so that helps set up here in 8.4 over a 10-year term structure and a yield structure what Jorion calls in this chapter the risk. So that's why I pulled this in to set this up, this column. The returns VAR is what he calls the risk for the fixed income portfolio. I hope that makes some sense, that it's the price volatility in the bonds that constitutes the risk, and that these are a function of the yield VAR and the modified duration. So that in his example of a 2-bond portfolio, this is Jorion 11.12, in this 2-bond portfolio we have 5-year terms. The compounding or coupon payout is annually, so that's a change from Tuckman. Another one of those just stylistic changes that we have to cope with. In Tuckman, all the coupons are semi-annual. Jorion here is using annual coupons. And so this first bond, you can see, pays a $6 coupon over 5 years. and then the face value of 100 at the 5th year. And the second bond has a $4 coupon, and then the return of principal at the end of the 1 year. So we have a 5-year bond and a 1-year bond. And those are the two cash flows for the 2-bond portfolio. And then we have a term structure of the 0 spot rate. So I'll show you why I have a gap here. I'll show you that in just 1 second. And then we've got Jorion's 3 mapping concepts, right? Again, just for the fixed income portfolio here. The most naive is to map single factor to the principal. And so each of these bonds has a face value of 100 or $200, $200 million in value. And I think that's also by design. I think that's actually the market value is 200 million. And so the 200 million here is mapped entirely to the portfolio's average maturity. We have a half of it really in 100 at 5 years. The other bond is a 1 year. 5 plus 1 is 6. Divided by 2 is 3. So the weighted average maturity of the portfolio is 3 years. And so you see how under this naive approach, we map all 200 million in value to the single primitive factor, which is a 3-year, in this case, a 3-year spot rate. So you see how it's a one way to do it. It's not going to be very accurate, but it is a way to summarize the 2-bond portfolio on the single factor. Now then a step up from that, also single factor, would be to map to the value to not the maturity, but the average duration, hence the gap here. And as you know, since these aren't 0 coupon bonds, the modified duration and the Macaulay duration is going to be less than the maturity. So we should expect a duration here of less than 3 years. And in Jorion's case, it's about 2.73 years here. So again, we take the 200 million in market value and map it to a primitive risk factor. In this case, the portfolio's weighted average duration of 2.73 years. And then finally, improving on both of the single factor measures to the most sophisticated, we map the present value of the bond of the portfolio's cash flows to each of these cash flow vertices, the set of vertices. And so now we're saying that the portfolio value responds to each of the spot rates in the term structure. And so we have 1, 2, 3, 4, 5. We're mapping to 5 term structure: the 1 year 0 rate, the 2 year 0 rate, the 3 year 0 rate, the 4 year 0 rate, the 5 year 0 rate. But also again, the sum. It's that we're mapping in sum the market value of the portfolio. And then 5C2 continues to illustrate a concept that Jorion goes into. And I mean, a good example of well, it's up to you how much time to spend on this, but you know, it's impossible for the exam to ask you to pre and post multiply the correlation matrix in order to produce the diversified VAR. But conceptually, Jorion's taken the 5-year term structure here, and then based on the present value of the cash flows in the portfolio, and then the individual VARs, so that's going to be that risk that we earlier looked at, the value risk of the price multiplied by the cash flow. So this is the individual VAR for each of our 5 primitives. And then he's introduced the idea of a correlation matrix or imperfect correlation between each of the 0 or spot rates in the term structure, right? So we have a 1 year, the correlation between a 1 year spot rate and a 1 year spot rate is 1. As usual, the correlation matrix is betrayed by a diagonal of 1s. But then we've got the term structure over here. And so he's implying here that there's going to be a high correlation between changes in the 2 year 0 or spot rate and the 1 year 0 spot rate. You think about that, makes some sense. A parallel move and shift in the term structure would be 1s everywhere. But then almost parallel moves should manifest as some high correlations. but he's introduced some imperfect correlation here into the term structure. And since in our sophisticated approach, we've mapped cash flow to each of those spot rates on the term structure, he's now introduced imperfect correlation between our portfolio's exposure to its risk factor, which ought to give us some diversification benefit. So in terms of adding the individual VARs, if we just add those up, we know we get the undiversified VAR, right? So that's a worthwhile concept here. Individual VARs, we add them up. In Jorion's case, we get a 2.63 undiversified VAR. Then introduce the correlation matrix, and then take the individual VAR, multiply by the correlation matrix, multiply by the transposed vector of individual VARs, so column vector, correlation matrix, row vector. This is going to give us the product of those three gives us a variance. Take the square root of that, and we get 2.57 million, which will be called here, or is called here in Jorion, the diversified portfolio VAR. So notice, so this is direct analog even just to the two asset portfolio. The undiversified VAR is the summation of the individual VARs, and is necessarily, when correlation is imperfect, greater than the diversified VAR. This 2.57 million picks up the benefit of everything that's less than 1 here in the correlation matrix. And right, so the matrix math in here is just several, just a generalized case of what we do in the two asset portfolio. But we get the diversified VAR and the benefit of the imperfect correlation. And then the aim is discuss how mapping of risk factors can support stress testing. And so there's a left panel and a right panel here. In the left panel, we've got the cash flows, a spot rate, and then a discount function, set of the discount factors that allows Jorion to compute the present value of the cash flows or the price of 200 million. So you see how we've got the two bond portfolio and its cash flows. Present valued or discounted by the term structure of spot rates gives us the market value of 200 million. And then Jorion's idea is that we take those risk variables, which again are the value at risk of the price, which was the value at risk of the yield. So just to start back, let me start that from the beginning again. Earlier sets up, Jorion assumes a yield volatility. That yield volatility multiplied by some deviatives informs a yield VAR. Then the yield VAR multiplied by the duration informs a price VAR. In other words, the worst expected change in price with some confidence, which he calls the risk. And then Jorion simply takes these risks, I don't know if I should say simply at this point, but takes these risks and shocks the discount factor by the risk. You see how the discount factor here moves down? So he's saying there's a risk of the discount factor shocking down by these amounts into this vector of discount factors, and then repricing at the present value, and notice getting a lower value as we'd expect. To me, it's not that low for a stress test. I would have expected, so interesting outcome given the methodology, right? We're only getting not even a $3 million deduction, but that's the methodology. We can, by mapping the portfolio to this limited set of risk factors, here's the risk factors, right? The term structure spot rates. All we're doing here then is shocking, really, the term structure, not totally unlike the key rate shift technique right here, except here there's no neighboring rates or interpolation. We're just doing straight off the 5 primitive risk factors, effectively shocking those up to lower the discount factor and then repricing the bond. Just a way to explore how the bond price could go down. I guess another way to look at this would be that if we just did a single factor yield to maturity, we could shock the yield and reprice the bond. So we see if the yield to maturity goes up by some basis points, how much does the price of the bond go down? That would be a stress test on a single factor. And here we've just done that but for each of the 5 spot rates that are our primitives. So Jorion has tracking error var that should be somewhat reminiscent of the tracking error in AMIC, which was the standard deviation of the difference between the portfolio and the benchmark. And then, so I'm going to make short. I'm not going to spend too much time. I'm just going to briefly here in the video go through the mapping of the other instruments. Because that fixed income, in this chapter, it's that fixed income portfolio that's the illustrative example for the concept of mapping, which is to say, again, breaking down that portfolio and mapping it to a limited number of risk factors and then manipulating the risk factors. But he says that we can similarly map to forwards, where the idea, again, this very thematic, we're taking the formula for the value of the instrument, right? So this is the value of the forward instrument. So now if we think way back to Jorion chapter 1, that distinction between valuation and risk measurement. Valuation is precise. It wants to solve for the value of the forward contract. Then what Jorion's doing here, basically with all of these, is taking the value of the forward contract, the formula for that, and saying, okay, if that's the value, then the inputs in that each of those variables must be a key risk factor. Basically extracting from this the risk factor. So we've got with and decomposing the long forward contract into 3 building blocks. Long the forward currency spot plus long a forward currency bill plus short a US dollar bill. And so here's got the valuation of this forward contract, and this is a currency contract. So he's basically said, let's say the 3 risk factors mapped here are the euro spot here, the euro bill rate or euro risk-free rate, and then we're short the US dollar rate, and that's the cash component here. 1, 2, 3, same risk factors that constitute the value, such that as exposure to these risk factors change, that'll impact the value of our forward contract. And then a similar correlation matrix exercise in order to produce the diversified value at risk. In this case, the sum of the individual VARs on the 3 risk factors is 6.16 million, and given some imperfect correlation, the diversified VAR exposure to the 1, 2, 3 risk factors is less at 5.74 million. The mapping of commodity forwards is significantly more complex, largely because the convenience yield is not tied to another financial variable. The risk measurement of commodity futures uses the following equation, where the primary driver of the value of the contract is the current forward price for the commodity. Forward rate agreements. I did replicate that example in the learning spreadsheet. And we can map to interest rate swaps. The key to mapping a complex or esoteric instrument is to first decompose the instrument into 2 or more constituent instruments. And so we know what to do with the swap, don't we? Because in the valuation, one of that 2 methods is to break that swap into its economic equivalent, a floating rate bond plus a fixed rate bond. So in this case, a floating rate note plus the leftover fixed cash flows. And then mapping options similarly can use the Black-Scholes pricing option methodology, and where we could have potentially up to the 5 primitive risk factors, although we might not use all 5 of those because some of them are less sensitive. So Jorion says a long position in an option consists of 2 building blocks: a long position in the stock equal to delta, plus a short position in the underlying asset financed by a loan. So for example, if the asset price is 100 and the delta is 0.536 for an at-the-money call option, where the call option is priced at $4.20, then the building blocks are we're long an asset, $53.60, plus short a finance positioned by a short position financed by $49.40. So you can see our key primitive exposure there, as you might expect, is exposure to the underlying asset price. And that's the end of video 5C. I look forward to sharing material in 5D. Thank you.